Hey guys, chapter 12. So chapters 1, 2, and 3, you guys just had an exam on that one. So now we're going to start chapter, not 12, chapter 4. There we go. So describing the relation between two variables. So here we have scatter, 4.1 is called scatter diagrams and correlation. So we're looking at response variables and explanatory variables. So the response variable is a variable whose value can be explained by the value of the explanatory variable or predictor variable. So something, a good example of this would be like medicine. So explanatory variable would be the amount of like milligrams that you take of, I don't know, Tylenol, versus a response variable, how bad your headache is on a level from 1 to 10. So explanatory variable is something that you're measuring, like both of them are measures. Response variable is just like the reaction to the explanatory variable. Draw and interpret scatter diagrams. All right, so a scatter diagram is a graph that shows a relationship between two quantitative variables. So quantitative meaning quantity, quantitative variables measured on the same individual. So each individual on the data set is represented by a point in the scatter diagram. The explanatory variable is plotted on the horizontal axis and the response variable is plotted on the vertical axis. So we're going to put our intermediate algebra or college algebra hats back on for just one more section. So here we have our like XY plane. And basically what they're saying is this bottom one is going to be our explanatory variable. Did I spell that right? Probably not. So explanatory variable, and this one over here is going to be our response variable. So explanatory variable, our cause and effect, our input versus our output. So depending on how you want to say it, this is going to be our explanatory variable, horizontal, vertical is going to be our response variable. And let's check out, I believe the next one is an example. Yep. All right, so a golf pro wants to investigate the relation between the club head speed of a golf club measured in miles per hour and the distance in yards that a ball will travel. He realizes that other variables beside club head speed determine the distance a ball will travel, so such as the club type, the ball type, the golfer themselves, weather conditions, a bunch of different things could go into changing that, changing the outcome. So to eliminate the variability due to these variables, the pro uses one single model of golf club, one golfer, and a clear 70-degree day with no wind. So once he has all of that, he's going to test it out, and this is what we end up with. So this really pretty table, let's go ahead and take a snapshot of the data so that way we could take it over to Excel. All right, and now with this, pro records. So draw a scatter diagram of the data. So I'm going to draw like a really quick sketch of this just so you understand how these numbers come to be. So here we said explanatory variable at the bottom, response variable going up and down. So explanatory variable is going to be the club head speed in miles per hour. The smallest value I see here is 99. So we're going to label them from 99 to highest one is 105. I see 105 and yep, just 105. So 100, 101, 102, 3, 4, and 5. That's 105. And all we're doing from here is matching club head speed with the distance. So looking at these values here, the smallest value, 58 to 57. Looks like it's 257. And the largest value, and I didn't put a little arrow over here, the largest value 277, 75. Looks like it's 277. So what I'm going to do is label these by fives. So we'll say that this is 255, 260, 265, 270, 275, and 280. So now we went above the largest one and below the smallest one. So we're going to capture all that data. And from here, the very first point that I'll draw is going to be this first point here. So response or explanatory variable of 100, response variable of 257. So 100, so 99, 100 is going to come off of this value here. And 257, we have 255 right here. 257 is going to be right above that right here. So we do that with all of the points here. Oh, and we end up with this graph. But since we're experts at this already, let's go ahead and bring it to Excel so that way Excel could do the work for us. So insert data from the table, from a file. Is it this one? Which one was it? Club head speed, miles per hour. Looks like it's this one. All right, looks good. Insert data anyway. All right, so now we have this, and to graph it, we would just highlight it, go over to insert, recommended tables, so we could kind of see what's going on here. Looks like this is what we want, a scatter plot. So we just want points. We don't want any lines or anything. And there we go. So it shows a relation between the two. So for 100, we have 257. 100, we have 257. Looks like it's that bottom one there. And another 100, 263. Looks like it's that one right there, just based on the way it looks. All right, and there we go. That's the relation between the two right there. This is what they got. So the scatter diagram is shown. It appears from the graph as club head speed increases, the distance the ball travels increases as well. So that makes sense, especially because from here, it looks like we could draw at least somewhat of a straight line where we have some points above, some points below that line. It looks like a really good, like a good graph, some sort of positive correlation that shows that as our speed increases, so does our distance. Wow, that looked terrible, but so does the distance. We would say that's positive correlation. So it's not always clear which variable should be considered the response variable, which one should be the explanatory variable. Scatter diagrams show the type of relation that exists between two variables. Our goal in interpreting the scatter diagram is to distinguish scatter diagrams that imply a linear correlation, a nonlinear correlation, or no relation at all. So it seems a little weird, but we could actually look at these right here and see the difference. So I'd say that this very first one, A, is a linear correlation because we could draw a line through some of the points, or we could draw a line between those points, showing that they do have some sort of relation. Everything is grouped kind of around that line. It's not specifically on that line, it's just around that line. And same thing for part B. So it's around that line, but not on that line. For part C, I do see some sort of correlation, but again, this one is not a linear correlation. Remember, this section is called linear correlation. But this one is not linear, so it's not a line. It's not something that we could just draw like that. It's something that we have to like curve in order to get that like sort of graph. Similarly, this graph here too, it looks like we are grouped around some sort of shape, but again, it's not a linear shape, even though we could draw these as linear shapes. So 1, 2, 3, it's 3 different lines that we're drawing. You guys weren't able to see that. So 1, 2, and 3. So it looks like we're able to draw lines and complete it, but it's still not a linear correlation because we still have to like lift up our pencil or stop that direction of the line that we're going. And part E, even though it looks like we could draw a line, it's kind of centered here. There isn't actual correlation here. So it just looks like the numbers are scattered all over the place. We can't really say that it's linear. So there's no relation in this case. So notice the difference between figure A and figure B. The data follow a linear pattern that's slant upward and to the right for figure A and downward to the right for figure B. Figure C and D show no linear relations. In figure E, there is no relation between the explanatory variable and the response variable. All right, two variables that are linearly related are positively associated when above average values of one variable are associated with above average values of the other variable. Below average values of one variable are associated with below average values of the other variable. That is, two variables are positively associated if whenever the value of one variable increases, the value of the other variable also increases. So all of this literally just said that we have positive, or we are positively associated if above average, so I'm going to say that this is above average here, of one variable are associated with above average of the other variable, above average over here. So we're saying that those points line up to this here. And they also mention below average. So I'm going to say this here is going to be considered below average. This here is also going to be considered below average. When we connect those 2 points, they increase from left to right. So that's what this last sentence talks about. So that is, two variables are positively associated if when the value of one variable increases, the variable of the other variable increases. So as we move to the right on this graph, so notice this here, the response ends up moving upward as well. So we're positively associated if one variable moves up, the other also moves up. And that's very different from negatively associated. So two variables that are linearly related are negatively associated when above average values of one variable are associated with below average values of the other variable. So let's get a picture that shows this relation. Above average values are associated with below average values. So that's 1 point there. And let's kind of look at the opposite. Above average values here are associated with below average values here. And we draw that line between those 2 points, showing that relation. So that's that first part. The second part, that is, two variables are negatively associated if whenever the value of one variable increases. So let's say this variable increases as we move forward this way. This variable is actually decreasing. So whenever the value of one variable increases, the value of the other variable decreases, and vice versa. So if we're looking at the increase of this right here, that's moving this way here, but here in our explanatory variable, it's decreasing. So everything is kind of backwards with this one. So this one is negatively associated because another way that we could see this is as we're moving from left to right, our variables are decreasing. Our graph is going down in a negative manner, meaning that they're negatively associated. Okay, so describe the properties of linear correlation coefficient. Ooh, finally some math. Okay, so the horizontal and vertical scales of the scatter diagram should be set so that the scatter diagram are not misleading to the reader. So again, this is going to kind of show a little bit of bias, and we're going to see that right here. So what we should not do is have this labeled, say like 0, this is 2, this here is 8, this is 100, this is 500, this is 1 million, and then show a linear correlation like this. So if we show this, it looks like things are positively associated in a linear manner. But over here, this graph on the side, or this scale on the side, does not reflect that. What that reflects is like a graph that's going up in an extreme manner. So that would be misleading. What you want to do is make sure that your scale is unified throughout the entire graph, both horizontally and vertically. Like you don't want it to show any sort of bias in any way. So do not mess with the scale like that. The scale should represent like a nice even scale. So numerical summaries of the bivariate data should be used in addition to the graphs to describe any relation that exists between the two variables. All right, so now the linear correlation coefficient or Pearson product momentum correlation coefficient. So we're just going to say linear correlation coefficient. So that is a measure of the strength and direction of the linear relation between two quantitative variables. The Greek letter rho represents the population correlation coefficient, and R represents a sample correlation coefficient. Represent only the formula for the sample correlation coefficient. So we're going to work with R. All right, so now looking at this sample linear correlation coefficient, where X, so what we're doing here is this variable here, this is going to be all of our data for our X value. So remember, explanatory variable. X is going to be our explanatory variable. Y is going to be our response variable. So what our action is, what our result is. So here, Xi represents each one of the data values. X bar is going to be the sample mean of that data set of the explanatory variable. S sub X is going to be the standard deviation of the X variable or the explanatory variable. Same thing over here. Y sub I is going to be all of the Y values minus Y bar is going to be all of, or the mean of the response variables. S sub Y is going to be the mean of the response variables. Since each one of these are like there's the exact same number of explanatory variables and there are response variables, both of them are going to be represented by n. And we're just going to, once we take the product of those two numbers, we're going to take the sum of all of those products and then divide it by n minus 1. So n, remember, is going to be the same for both of them because we can't have a response variable and not a, or we can't have a response variable and not an explanatory variable, and vice versa. All right, let's take a look at the data. This is another, so an equivalent computational formula for the linear correlation coefficient is this right here. We're not going to do all of this. This one looks a little bit too complicated. All right, properties of the linear correlation coefficient. So the linear correlation coefficient is always between -1 and +1 inclusively. So that is -1 is less than or equal to R, which is less than or equal to +1. So they're all going to be between -1 and +1. If R is equal to a +1, then a perfect positive linear relation exists between the two variables. If R is equal to -1, then a perfect negative linear relation exists between the two variables. The closer R is to +1, the stronger is the evidence of the positive correlation between, that kind of sounds, the closer R is to +1, the stronger is the evidence of positive association between the two variables. The closer R is to -1, the stronger is the evidence of negative association between the two variables. So +1, positively associated, -1, negatively associated. If it's not equal to those, but still shows it's still large enough or still small enough, then that's what they're talking about there. If R is close to 0, then there is no evidence, or then little or no evidence exists of a linear relation between the two variables. So R close to 0 does not imply no relation, it just implies no linear relation. And we'll see a couple examples here soon. The linear correlation coefficient is unitless is a unitless measure of association. So the unit of measure for X and Y plays no role in the interpretation of R. The correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. All right, now looking at this. So positive, perfect linear correlation. We're saying that R is equal to 1. So notice that when I draw this line, we could draw all the points on the exact same line. So part B is showing positive linear correlation, like strong positive linear correlation. Notice that when we draw this line here, we could see that everything is grouped really tightly together. There are some points that are not on that line, but it's still close enough to that line that we could say there's a line that represents that data. Over here for part C, it kind of looks a little bit weaker. Still somewhat grouped together, we are able to kind of push the entire data set through that line and say that it's roughly around the same thing. For part D, perfect negative linear relation. So looking at this value here, I know it's drawn just a little bit below all the points, but we could see that we could draw a line perfectly through all the points. All the points end up on that line, not this red one that I just drew, but a line. Same thing over here for part E. We're able to draw a line. Some of the points are above that line, some points are below that line, but there's still strong correlation along that line. Next is part F, still same thing. So we just finished our chapter 3, right? So we could consider this one an outlier, maybe a little off. This one here might be a little bit off, but not so much. But here we might have some outliers, we might not. But here we could still show that sort of pattern from one to another. Now looking at part G, I'd say that there's no relation here because there isn't like a shape or anything that I could draw that would catch majority of this data. If you look at part H, we could draw a parabola and say that it follows that parabola. It's not linear, so definitely non-linear, but there is some sort of pattern there, unlike this one here. So I mean, we could draw like a really ugly scribble like that and say that it follows that sort of shape. It's not linear, it's a relation of some sort, but I would say there's no linear relation in that data set. All right, suppose the data are equally dispersed on 4 quadrants and the negative products resulting from the data in quadrants 2 and 4 will offset the positive products resulting from data in quadrants 1 and 3, resulting in quadrants 1 and 3. So the result is a linear correlation coefficient close to 0. So all they're saying is looking at this data set right here, they'll offset each other and it'll look as if some of the data is represented by a positive number. So if we had some values over here, some values over here, showing no correlation, things could mess up this data set if they aren't read properly. So it's still holding like that positive and negative value here and there. There shouldn't be that many problems like this in your homework though. All right, compute and interpret linear correlation coefficient. All right, so for the data shown in table 2, compute the linear correlation coefficient. A scatter diagram of the data is shown in the figure. The dashed lines on the scatter diagram represent the mean of X and the mean of Y. All right, so let's grab this data here, take a picture of it. And let's take it to Excel. All right, so from here, we'll go to insert data from picture, picture from file. It would be this one. There we go. All right, so this looks like an I, it should be 1. Everything else looks good, so we'll just insert it either way. All right, now that we have this, let's make it look a little bit better. I hate that it's making this part larger. All right, much better. Okay, so now this, way better. All right, so now that we have this here, what we're gonna find are the different variables. Okay, so let me get our formula. So R is equal to the sum of each of our data values, xi minus x bar, and we're dividing this whole thing by s sub x, so the standard deviation of our x variable. And over here, it's the same stuff, but for y. So y sub I minus y bar divided by s sub y. And now that we have all of that, we get the product of those two, sum, and we divide this whole thing by n minus 1. All right, since we have all of these, x sub I, we have those already. That's all of the x values. Y sub I, we have all of those, all the y values. X bar, so we have to figure out what x bar is. So that's going to be the average of all of the x values. And we're going to find the standard deviation of all the x values. So looking at that first, let's do it over here. So we have x bar, then we have s sub y. And we're going to have those two values, and then we'll also have y bar and s sub y. All right, so x bar, that's equal to the average. So average of the x values. So average of these values right here. Cool. S sub y is equal to the standard deviation. So STDEV. Ooh, but is a standard deviation of the population or a standard deviation of the sample? So it's going to be standard deviation of the sample because this is a sample set. This is just a sample of what, actually, it's not the club head speed or anything. It's just a sample of the data. Right here, y bar is going to be the average of the y values. And here, this is going to be the standard deviation of the sample, not population, sample of the y values. All right, so we have those. Next thing we have to do is figure out what this value is for each of the data values. So here, what we're going to do is say this is x sub I minus x bar, and we're dividing that by s sub x. So again, here, this is going to be equal to our numerator. So the numerator is equal to our x value minus the mean, x bar. And close parentheses, we're dividing that by our standard deviation. All right, so notice these values here. For all of them, the mean and also the standard deviation are not going to change. It's going to be the same for all of these values. The only thing that should change is the x value as we bring them down. So from here, we're going to grab that corner. So click on the corner and drag it down. Perfect. So now that's all of this. That's this whole part. So the next one we're going to do is the same thing, but for y. So this is going to be y sub I minus y bar divided by s sub y. So here equal to the numerator. So let's put parentheses for the numerator. y1 minus y bar. And we're closing the parentheses and dividing by the standard deviation of y. And there we go. But now here, what we're going to do is the same thing. So x bar is the same thing, or I'm sorry, y bar is the same thing for each of these values. So we're going to put dollar signs around that. and dollar signs around our standard deviation, because those values are going to be the same for all of these. The only thing we want changing is y itself. And there we go. All right, so far we have this value here for each of the values. We have this value here for each of the values. So now we're going to get the product of those two. Once we have that, we'll add all those together and see what we get. So I'll do that over here. So again, this is going to be x minus x bar over s sub x times y minus y bar over s sub y. So multiplying those two columns together, so equal to this value times this value here. And these are individuals here, so we could just grab the corner, drag it down. It's going to give us a product of each of these together. So like this last one is a product of these two together. Perfect. All right, so we have the product. Next thing we have to do is find the sum of all of those variables, or sum of all of the products. So one value is going to represent that. So we have the sum of xi minus x bar over s sub x times yi minus y bar over s sub y. And that value we'll just type over here instead. So equal to the sum of all of these values here. Now, lastly, to record what r is, it's going to be this number, which we just found, and divided by n minus 1. So n minus 1, here we have 6, but the first column or the first row is not data, so we have 5. So here we're going to say that r is equal to this value divided by 5 minus 1. And that gives us a negative 9 or negative 0.9456. So let's see if we missed anything over here. So for the data shown in table 2, compute the linear correlation coefficient. A scatter diagram of the data is shown in the figure. Dashed lines in the scatter diagram represent the mean of x bar. I'm sorry, represent the mean of x and the mean of y. So that's, they just drew that same thing that we did over here. Which one was it? Oh, we didn't draw anything. Let's go ahead and get that. So insert graph. We do that here. And what they did is they saw, let's see, do we still have that? Yeah. So they saw that x bar is equal to 4. How do we show that? So x bar is equal to 4. So they just drew a line here. Y bar is equal to 10. So this is our 10 value. They just drew another line right there. So that's all they did here. And now with this, they showed all the steps that they took to find these values. Divided it by n minus 1, we got this value here. So we will agree to round the correlation coefficient to about 3 decimal places. And we'll kind of see why in a couple of slides. So the correlation coefficient suggests strong negative association. So strong because it's really close to 1, so 0.946. And negative because it has that negative number in the front. So the correlation coefficient suggests a strong negative association between the two variables. So use the statistical spreadsheet or a graphing calculator with advanced statistical features to draw a scatter diagram of the table. Determine the linear correlation between club head speed and distance. All right, so we did that. We graphed it. Wow, such a beautiful graph. Let's get rid of that. But now let's say we don't want to do all of this crazy stuff here, right? So another way that we could actually find these values are equal to correlation coefficient, so CORREL is going to be the command for this. So our explanatory variable here, comma, our response variable here, and hit enter, and it gives us the exact same number. So we don't have to go through all of this crazy computation. All we have to do is type it into Excel, and Excel will do the work for us. And let's see, yep, exact same thing. Ooh, sorry, but this is for the club head speed and distance. So club head speed came from this data right here. And we already have it graphed, beautiful. So let's find the correlation coefficient for this one. So R equaling the correlation coefficient. So this is equals CORREL for correlation coefficient of the club head speed, comma, distance. And our correlation coefficient is 0.938. Awesome. So that makes sense because from left to right, we're increasing. So as our explanatory variable increases, so does our response variable. So makes sense here. And let's see what else. All right, so figure A shows a scattered diagram. Figure B shows the linear correlation coefficient obtained from Excel. Cool, that's exactly what we did. Because the linear correlation coefficient is positive, we know above average values of X, club head speed are associated with above average values of Y, driving distance, and below average values of X associated with below average values of Y. So that's linear correlation, beautiful. So I'd say that's strong linear correlation. All right, so determine whether a linear relation exists between two variables. So basically what that's asking is this number actually significant, or is it not so significant as we are, not as significant as we think? So step one, determine the absolute value of the correlation coefficient. And remember, absolute value is just the distance away from zero. So it's a positive number, whether the correlation coefficient is negative or positive, just measuring the distance from zero. Step two, find the critical value on table 2 from Appendix A for the given sample. Step three, if the absolute value of the correlation coefficient is greater than the critical value, then the linear relation exists between the two variables. Otherwise, no linear relation exists. All right, if the correlation coefficient is positive and greater than the critical value, the variables are positively associated. If the correlation coefficient is negative and less than the opposite of the critical value, the variables are negatively associated. So using the results from a previous example, determine whether the linear relation exists between club head speed and distance. So we're going to use this to determine whether it's significant or not. All right, so let me show you how to find that in your book. All right, so here we have Pearson or MyStatLab. For the book, like for your assignments, you would come over here. They're listed right over here as soon as it loads. But what we're looking for is the book. So contents. So looking at this, all of this looks like it might not be exactly or maybe it is. Anyway, let's go up here to text that mirrors our textbook or your textbook. And it loads to this first initial page that's kind of loading. All right, so from here, we're going to go over to table of contents and scroll all the way down, Appendix A, tables. Perfect, that's exactly what we need. And what we're looking for is the correlation coefficient table, which is this one here. So it's a second table. So table 2, correlation coefficient. So critical values for correlation coefficient. And let's see what we're looking for. Okay, so using the results from a previous example, determine whether the linear relation exists between club head speed and distance. All right, so let's grab all the data that we're going to need for this problem. First is going to be our correlation coefficient that we got for this problem. So in this case, R. So we'll say R is equal to 0.938. So 93869. So 9387. And our correlation coefficient. So one thing we have to get is how many values we have. So we have 1, 2, 3, 4, 5, 6, 7, 8. So N is equal to 8. And let's come over here to see what our value is. So our critical value, so we'll write that here. So the critical value for N equaling 8 is 0.707. And see why they wanted 3 decimal places for our correlation coefficient, just to see if it falls into the same category as this. So looking at that, coming right back here, we have R equal to 0.9387. And remember, the first thing that they want us to do is get the absolute value. So now the absolute value of R is equal to the absolute value of 0.9387. which is just going to be a positive 0.9387. And now what we're looking at here is if this value is larger than our critical value, then it's large enough for us to say that there's a correlation. So here, linear correlation coefficient, they went out 3 decimal places instead of 4, but they got 0.939. Absolute value of 0.939 was 0.93. We got something just a tiny bit different. Step 2, table 2 shows a critical value with N equaling 8 is 0.070, which is this value that we got here. Beautiful. Next, what we're looking at is the absolute value of 0.939 being greater than 0.707. So here, since it is greater, so since 0.939 is greater than, it's a bigger number than 0.707, a positive association exists between club head speeds and distance. So there's strong positive linear relation between the two. So now, why is this significant? Because, wrong one. So the reason why this is significant is because we could ask ourselves, like, what number is good enough? So what number is good enough to say that there's some sort of relation between the two? And that should change between a bunch of different values, right? So 3 values having the exact or having strong correlation together should not have the same amount as, like, say 30 values, right? So whenever we have 3 values, 3 is it's a pretty small number. So even if we look at like heights within the family, if we only look at the 3 tall people in the family, it's going to kind of like force us to think a certain way about the height in the family, right? So 3 isn't that significant of a number in statistics at all. So when we're looking at correlation coefficients, when we have 3 values, we need that correlation coefficient to be extremely high for us to prove that those 3 have some sort of relation to each other. That's why with 3, our critical value for the correlation coefficient is 0.997. So they have to be really, really, really close to each other in order for us to even consider that there's some sort of relation between the two. Now we start getting to numbers a little bit higher, let's say 6. Between 6 numbers, correlation is not going to be exact between 6 numbers. So there we draw the line at 0.811. So 0.811, it's still a pretty large number, but it's still giving us a little bit of room to play with over here. Now down here with 30, we're probably not going to have that many things in common once we get 30 different values or even higher than 30 different values. With 30 plus values, there's going to be so many different values that could possibly alter the alter the numbers. So we're going to be a lot more lenient with that. So here our critical value for 30 plus is 0.361. So less correlation, even though when I look at this right here, I say 0.361, that number isn't significant enough. Like I don't want that number to distinguish whether or not there's some sort of correlation between the two. No, what we're looking at here, super strong correlation because it's only 3, but here we're giving it the opportunity to have a couple of points left astray or left in different places. So we're giving it the opportunity to have like 30 different points kind of thrown all over the place. 30 different points. I'm pretty sure I'm drawing more than 30 here, but see how there's still positive correlation here versus us trying to say that there's positive correlation between 1, 2, and 3 points. So there should still be some sort of positive correlation there, but it shouldn't have to be exact, if that makes sense. All right, so going back to this, so because it is greater than 0.707, we do have positive association or positive linear relation between the two variables. All right, so this here, so explain the difference between correlation and causation. So this here is, I'd say, the most important part of statistics because it doesn't matter what your numbers tell you. There could be some sort of other variables that you're looking at that aren't exactly true for these data values. All right, so if data used in a study are observational, we cannot conclude that two correlated variables have a causal relationship. So lurking variable, a lurking variable is related to both the explanatory variable and the response variable. So for example, as air conditioning bills increase, so does the crime rate. Does this mean that folks should turn off their AC so that the crime rates decrease? Certainly not. In this case, a lurking variable is air temperature. So as air temperature rises, both air conditioning bills rise and crime rates rise. So lurking variable could force a certain thing to happen. So that way we could look at the two different relations and in our head say that the two relations are one causes another, but in reality, it's not causation, it's correlation. So correlation does not imply causation. Just because we turn our AC on does not mean that people are going to murder us in our homes, or what was it, break-ins? Crime rates. It's not going to cause crime rates to go through the roof. So it's just one thing happening and also another thing happening around the same time. So causation does not represent correlation. All right, so looking at this, because cola tends to replace healthier beverages and colas contain caffeine and phosphoric acid, researchers Catherine L. Tucker and associates wanted to know whether cola consumption is associated with lower bone mineral density in women. Table 4 lists the typical number. Table 4 lists the typical number of cans of cola consumed in a week and the femoral neck bone mineral density for a sample of 15 women. The data were collected through a prospective cohort study. All right, looking at this, so we graphed it. Oh, and since we're experts, let's just grab that data and graph it. All right, we could bring it over here. So insert data from table, picture from file, and it should be one of the latest ones that I took. Yes. Just making sure these look about the same. All right, looks good enough to me. So insert anyway. All right, so looking at this data here, let's insert scatter plot and let's get this done. All right, cool. So here it looks like we have negative correlation. Let's see if our correlation coefficient concurs with that. So correlation coefficient R, and this is equal to CORREL for correlation. And it's going to be this data set here, comma, this data set here, whether we could see it or not. There we go. All right, so negative 0.805, negative correlation. All right, I like it. Let's see, 16. The first one is words, so it's 15. Let's see what this says, 15, 0.514. So I'd say that this is strong negative correlation, negative because it's going downward and it's a negative number here. So I'd say there's strong negative correlation. So now let's get back to the lecture. So because COLAs, okay, so the data were collected through Prospective Cohort study. Fun. The figure shows a scatter diagram of the data. Correlation between number of COLAs per week and bone mineral density is 0.806, which is what we ended up getting over here. Let's see. And because it's greater, the absolute value of negative 0.806 is greater than 0.514, we conclude a negative linear relation exists between the number of COLAs consumed and the bone mineral density. So because the data says it, I'm going to say that in my head, or at least based on what the data says, that the more COLAs that you drink, the lower your bone mineral density is. But can the author conclude that the increase in number of COLAs consumed causes a decrease in bone mineral density? Identify some lurking variables in the study. So remember, lurking variables are something that is related to both the explanatory variable and the response variable. So something that relates the two, I would say, is a diet. So if someone has a diet that they're consuming like a great amount of COLAs each week, maybe their diet isn't exactly what it should be. Maybe it's somewhat of an unhealthy diet. So that could be one of the causes of the bone mineral density, or a decrease in the bone mineral density. Another lurking variable could be age. We don't really know exactly how old the women are that are in this study. Another thing that could affect it is their like prior history. So we don't really know much about their prior history, or we don't have like blood work on their prior history or anything like that. So, or I'm guessing we don't, but let's see what some of the other ones are. So in prospective cohort studies, data are collected in a group of subjects through questionnaires and surveys over time. Therefore, the data are observational. So we're not actually, like, we didn't go in there studying them beforehand. We just studied them like specifically at those times and kind of witnessed a change. So the researcher cannot claim that the increase in COLA consumption caused the decrease in the bone mineral density. So in their article, the author identified a number of lurking variables that could confound the results. So age, body mass index, like BMI, height, whether they were smokers, average daily intake of alcohol, maybe they were drinkers, calcium, caffeine, total energy intake, physical activities, season of measurements, estrogen use, menopause status. So there's a bunch of different lurking variables that could like kind of sway the results one way over another. So we don't know exactly whether or not the soda had a decrease in mineral bone density. The authors were careful to say that increased COLA consumption is associated with, so it's not a cause, but it is associated with lower bone mineral density because of potential lurking variable. They never stated that increased COLA consumption causes lower bone mineral density. So again, it's causation, not, or it's correlation, not causation. One did not cause the other. The two are correlated to each other or associated with each other. And there we go. That's the end of 4.1. And this is the only section that we're going to go over in chapter 4. So if you guys have any questions on this, go ahead and let me know. Send me an email. But if not, good luck on your homework, guys. Bye.